Good morning, all of you. Today I am going to make an audio recording for visual impaired students of Physical Chemistry book of Dr. S.C. Ketapal Pradeep book. Chapter Electrochemistry Section A Electrical Transport 6.1 Electrolytic and Metallic Conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through are known as insulators. Conductors are divided into two classes. First, those which conduct electricity without undergoing any decomposition. These are called electronic conductors, that is, metals, graphite, and certain minerals. As the name indicates, the conduction in this case is due to the flow of electrons. Second, those which undergoes decomposition when current is passed through the aqueous solution or melt. These are known as electrolytic conductors or electrolytes. Example: solution of acids, base, and salts in water, fused salts, etc. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into two main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acid, that is HCl, HNO3, H2SO4, etc. Strong bases, that is NaOH and KOH, etc. and most of the inorganic salts. This dissociate almost completely in the aqueous solution or in the molten state and has conduct electricity to a large extent. Weak electrolytes are substances like weak acids, example CH3COOH, HCN, H2CO3, H3PO4, etc. and weak bases, example NH4OH, CaOH twice, AlOH thrice, etc. These have low degree of dissociation and hence conduct electricity to a large extent. Substances like sugar, urea, etc., the solutions of which do not conduct electricity are known as non-electrolytes. Factors affecting electrolytic conduction. The conductance of the solution of an electrolyte depends upon the following factors. First, interionic attractions, which depends upon the interactions between the ions of the solute and hence are called solute-solute interaction. On the basis, the substances are classified as strong electrolytes and weak electrolytes as already mentioned. Second, solvation of ions, which depends upon the interaction between the ions of the solute and the molecules of the solvent and hence are called solute-solvent interaction. Third, viscosity of the solvent, which depends upon the solvent-solvent interaction. The effect of all these factors decreases with increase of temperature. Hence, the electrolytic conduction increases with increase of temperature. On the other hand, the electrical conduction of the electronic conductors decrease with increase of temperature. Alternately, the factors on which the electrolytic conductance depends are as follows. First, nature of the electrolyte. Strong electrolytes ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity also to a small extent. Second, nature of the solvent. Electrolytes ionize more in a polar solvent, hence greater is the polarity of the solvent, greater is the ionization and hence greater is the conduction. Third, concentration of the solution. Higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte the ionization is less, whereas in a strong electrolyte the interionic attractions are higher at higher concentration. With dilution, interionic attraction decreases and hence conduction increases. 4. Temperature. On increasing the temperature, the dissociation increases and hence the conduction increases. Difference between metallic conductors and electrolytic conductors. The main point of difference between metallic conductors and electrolytic conductors may be summed up in Table 6.1. Table 6.1. Difference between metallic conductors and electrolytic conductors. Metallic conductors, electrolytic conductors. First, flow of electricity takes place without the decomposition of the substance. First, flow of electricity takes place accomplished by the decomposition of the substance electrolyte. Second, flow of electricity is due to the flow of electrons only, that is, there is no flow of matter. The conductance depends upon the structure and density of the metal and the number of valence electrons per atom. Second, flow of electricity is due to the movement of ions and hence there is a flow of matter. Third, the electrical conduction decreases with increase of temperature. This is because kernel starts vibrating, which produce hindrance in the flow of electrons. Third, the electrical conduction increases with increase of temperature. This is generally due to the increase in dissociation or decrease in the inter-ionic attraction. Fourth, the resistance offered by metal is also due to vibrating kernels. Fourth, the resistance shown by an electrolyte solution is due to the factors like inter-ionic attractions, viscosity of solvent, etc. 6.2. Electrical resistance and conductance. Every substance offers resistance to flow of electricity to a small or large extent. The law that gives the exact value of the resistance is known as Ohm's law. It states that in addition to metals, graphite and certain minerals also conduct electricity due to the presence of free electrons in them, hence they are collectively called as electronic conductors. If to the end of a conductor a voltage E is applied and a current I flows through it, then the resistance R of the conductor is E by I. Current is generally measured in amperes, whereas voltage is measured in volts. If 1 ampere current flows through a conductor, when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm, written as 1 ohm. Thus, according to Ohm's law, R is equal to E by I, or ohms is equal to volt by amperes. In terms of SI base unit, ohms is equal to kg meter square per s cube a cube. This is explained below. Ohms is equal to volt by ampere is equal to work per unit charge by ampere is equal to work by divided by charge is into 1 by A is equal to F into L divided by A into S into 1 by A is equal to M into A into L divided by A square S is equal to kg into meter per second square into m divided by a square s is equal to kg meter square divided by s cube a square. It is seen that like metallic conductors, solutions of all electrolytes also obey Ohm's law. It is obvious that a substance which offers greater resistance will allow less electricity to flow through it. This result as follows from Ohm's law, according to which I is inversely proportional to 1 by R. The reciprocal of the electric resistance is called the conductance. This is usually represented by C. Thus C is equal to 1 by R. It is a common practice to speak of the conductance of a solution rather than its resistance unit. The unit of conductance are Siemens or reciprocal ohms, written as ohms inverse or MHO or RO. IS is equal to 1 ohm inverse. For example, if a solution has a resistance of 10 ohm, it is said to have a conductance of 1 by 10 ohm inverse or 1 by 10 MHOS or 1 by 10 ohm inverse or 1 by 10 Siemens. 6.3 Specific equivalent and molar conductivities. 6.3.1 Specific conductivity, or simply called conductivity. It is observed that resistance R of a conductor is first directly proportional to its length L of the conductor and second inversely proportional to its area of cross section A. That is, R inversely proportional to L by A, or R is equal to PLA by A, where P is the constant of proportionality called specific resistance or resistivity. Its value depends upon the material of the conductor. The reciprocal of resistivity is also known as specific conductivity or simply conductivity. It is denoted by kappa, K, or K. Thus, if K is the specific conductivity and C is the conductance of the solution, then R is equal to 1 by C and resistivity is equal to 1 by kappa. 1 by C is equal to 1 by K into L by A is equal to K is equal to C into L by A. Now, if L is equal to 1 centimeter and A is equal to 1 square centimeter, then K is equal to C. Hence, specific conductivity of a solution is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of the cross section. Alternately, it may be defined as conductance of 1 centimeter cube of the solution of the electrolyte, figure 6.1, or in terms of SI base unit, it is defined as the conductance of 1 meter cube of the conductor. If the volume of the solution is V centimeter cube, the specific conductivity of such a solution at this dilution V is written as Kv. Similarly, at concentration C, it is represented as Kc. Unit resistivity P is equal to R into A by L is equal to ohm centimeter square divided by centimeter is equal to ohm centimeter or ohm centimeter or ohm meter in SI unit. 1 ohm meter is equal to 100 ohm centimeter. Specific conductivity K is equal to 1 by resistivity is equal to 1 by ohm centimeter is equal to ohm inverse centimeter inverse or ohm inverse centimeter inverse or S centimeter inverse or S meter inverse in terms of SI unit. 1 S centimeter inverse is equal to 100 S meter inverse. 6.3.2 Equivalent conductivity. For comparing the conductance of the solution of different electrolytes, it is essential that first, the volume of the solution should be same, and second, they must contain such a definite amount of the electrolyte which gives ion carrying the same total charge. The best choice is therefore to consider the solution having equal volumes and containing their corresponding gram equivalent weight. The conductance of such a solution is called its equivalent conductivity. Hence, equivalent conductivity of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of the solution when the distance between the electrodes is 1 centimeter and the area of the electrodes is so large that whole of the solution is contained between them. It is represented by lambda equivalent. Relationship between equivalent conductivity and specific conductivity. The equivalent conductivity of a solution is usually not found directly but is calculated from the specific conductivity. The relationship between equivalent conductivity and specific conductivity may be obtained as follows. Consider a rectangular vessel with its two opposite walls and 1 centimeter apart and made of some metal sheets so that these act as the electrodes. Case 1. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken in the vessel. The conductance of this solution will be then its specific conductivity. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be its equivalent conductivity by definition. Thus, 1 centimeter cube of the solution containing 1 gram equivalent of the electron is considered the equivalent conductivity is equal to its specific conductivity. Case 2. Suppose 4 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken. The conductance of the solution will be still equal to its equivalent conductivity at this dilution. But now there will be 4 cubes, each of volume 1 centimeter cube as shown in figure 4.6.2. The conductance of each 1 centimeter cube of the solution is equal to its specific conductivity, so that the total conductance of the solution, that is equivalent conductivity, is 4 times the specific conductivity. In general, if the volume of the solution containing 1 gram equivalent of the electrolyte is V centimeter cube, we have equivalent conductivity is equal to specific conductivity into V. Lambda equivalent is equal to kV into V. In terms of concentration, if the solution has a concentration of C gram equivalent per liter, that is C gram equivalents are present in 1000 centimeter cube of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 by C. Hence, the above expression may be written as lambda equivalent is equal to Kc into 1000 divided by C equivalent is equal to Kc into 1000 by normality. Note carefully that in the above expression V is the volume of the solution in centimeter cube containing 1 gram equivalent of the electrolyte and C is the concentration in gram equivalent per liter. Lambda equivalent is equal to K into V is equal to ohms inverse, centimeter inverse is equal to centimeter cube by gram equivalent is equal to ohm inverse centimeter square gram equivalent inverse, or ohm inverse centimeter square equivalent inverse, or S centimeter square equivalent inverse, or S meter square equivalent inverse in SI unit. 1 S meter square equivalent inverse is equal to 10 power 4 S centimeter square equivalent inverse. 6.3.3 Molar conductivity. The molar conductivity of a solution is defined in a manner similarly to that of the equivalent conductivity as under. The molecular conductivity of the solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolyte dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of electrodes is so large that the whole of the solution is contained between them. It is usually represented by lambda m. Relationship between molar conductivity and specific conductivity. As in the case of equivalent conductivity, the molar conductivity is related to the specific conductivity as follows. Lambda m is equal to kV into V. Lambda m or lambda m is equal to Kc into 1000 by C is equal to Kc into 1000 by molarity, where K is the specific conductivity and V is the volume of the solution containing 1 mole of the electrolyte, and C is the molar concentration, that is mole liter inverse or mole dm minus in 3 unit. Comparing with the equivalent conductivity, the unit of lambda m will be ohm inverse centimeter square mole inverse or S centimeter square mole inverse, or ohm inverse centimeter square mole inverse, or S meter square mole inverse in SI unit. 1 S meter square mole inverse is equal to 10 power 4 S centimeter square mole inverse. 1 S centimeter square mole inverse is equal to 10 power minus 4 S meter square mole inverse. 6.4 Measurement of electrolytic conductance, specific conductivity, equivalent conductivity and molar conductivity. First, electrolytic conductance. Conductance is the reciprocal of resistance, and the conduction conductance can be obtained by the measurement of the resistance, and the later can be found by the principle of Whetstone bridge method shown in figure 6.3. It contains four arms containing the resistance R1, R2, R3 and R4. R1 is the variable resistance and R2 is the unknown resistance. When null point is obtained, that is, there is no deflection in the galvanometer G, R1 divided by R2 is equal to R3 divided by R4. Knowing the value of R1, R3 and R4 and R2 can be calculated. In finding the resistance of the solution of an electrolyte, a special type of a cell has to be used such that the solution is present between the two electrodes. The cell thus used is called conductivity cell. It is made up of Pyrex glass and has two platinum electrodes at a fixed distance apart, shown on right hand side of figure 6.4. The most serious problem in the measurement of resistance and hence the conductance of the solution of an electrolyte is that if direct current is used, it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrodes changes, with this result in the change in the resistance of the solution. This effect are called the polarization effect. To overcome this problem, an alternating current in the audio frequency range of 550 to 5000 cycles per second is used. However, when the alternating current is used, ordinary galvanometer fails to detect the null point. Hence, the galvanometer is replaced by earphone. Further, to minimize the polarizing effect, the electrodes are coated with platinum black, that is finely divided platinum deposited on the electrodes electrolytically. To sum up, three modifications required in the usual Wheatstone bridge method are: first, source of direct current is replaced by a source of alternating current, which is either an induction coil or a vacuum tube oscillator, which is quieter and gives a more symmetrical current. Second, galvanometer is replaced by an earphone. Third, electrodes of the cell are coated freshly with platinum black before use. The complete assembly for the measurement of electrolytic conductance is shown in figure 6.4. A suitable value of the resistance R is introduced from the standard resistance box such that when the sliding contact, that is the jockey J, is moved along the stretched wire, the sound in the earphone is reduced to minimum at a point somewhere in the middle of the wire AC, say at the point D. Then, if X is the resistance of the electrolytic solution by Wheatstone bridge principle, resistance R divided by resistance X is equal to resistance of wire AD divided by resistance of wire CD is equal to length AD divided by length CD. Resistance X is equal to resistance R into length CD divided by length AD. Thus, knowing the resistance at the balance point D, the resistance X of the electrolytic solution can be calculated. Then, conductance C is equal to 1 by X is equal to 1 by R into length AD divided by length CD. Second, specific conductivity. Specific conductivity, or simple called conductivity K, is related to the conductance C according to the expression K is equal to C into L by A. Thus, the specific conductivity of a solution can be determined by measuring its conductance and the distance L between the electrodes and the area of cross section A of each of the electrodes. But it is not convenient to measure L and A accurately. However, for a particular cell, L divided by A is a constant, and this constant is called cell constant. That is, L divided by A is equal to cell constant. Specific conductivity K is equal to conductance into cell constant. Thus, the cell constant of any particular cell can be found by measuring the conductance of the solution whose specific conductivity is known. For this purpose, generally specific conductivities of KCl solution are used, which are known accurately at different concentration and temperature. For a few concentrations at a temperature of 298 Kelvin, these values are given below. Concentration of KCl solution. Conductivity, specific conductivity 1.000 m or 1000 mole meter minus 3. 0.1113 s centimeter inverse or 11.13 s meter inverse. 0.100 m or 100 mole meter cube minus cube. 0.0129 s meter inverse or 1.29 s meter inverse. 0.010 m is or 10 mole m minus 3. 0.00141 s centimeter inverse or 0.141 s meter inverse. Knowing the value of the cell constant, the specific conductivity of the given solution can be determined by measuring its conductance and multiplying the value with the cell constant. Third, equivalent conductivity. Equivalent conductivity, lambda equivalent, is related to the specific conductivity K according to the equation. Lambda equivalent is equal to K into 1000 by C equivalent is equal to K into 1000 by normality, where C equivalent is the concentration of the solution in gram equivalents per liter, that is the normality of the solution. Thus, knowing the normality of the solution and the specific conductivity K, lambda equivalent can be calculated, where C equivalent is the concentration of the solution in gram equivalents per liter, that is the normality of the solution. Thus, knowing the normality of the solution and the specific conductivity K, lambda equivalent can be calculated. For fourth, molar conductivity. The molar conductivity is related to the specific conductivity according to the relation. Lambda m is equal to K into 1000 by Cm is equal to K into 1000 by molarity, where Cm is the molar concentration. Thus, knowing where Cm is the molar concentration, thus knowing molar concentration C and the specific conductivity K, lambda m can be calculated. Conductivity water. For the accurate result, the solution should be prepared in a specific purified water whose own conductance is very small. Such water is called conductivity water. Alternatively, to get the resistance of the electrolyte, the resistance of water used for making the solution may be determined and then subtracted from the resistance of the solution. 6.5 Variegation of conductance, specific conductivity, equivalent conductivity, and molar conductivity with dilution. In general, electrolytic conduction as well as the equivalent conductivity and molar conductivity increase with dilution, whereas the specific conductivity of an electrolyte solution decreases with dilution. The reason for such a behavior and brief explained below. The conductance of a solution is due to the presence of ions in the solution. The greater the number of ions, the greater is the conductance. As on dilution, more ions are produced in solution, so the conductance should also increase on dilution. The specific conductivity of an electrolyte falls with dilution because the number of current carrying particles, that is ions, present per centimeter cube of the solution become less and less on dilution. However, the increase of equivalent and molar conductivity on dilution is due to the fact that these are the products of specific conductivity and the volume V of the solution containing 1 gram equivalent or 1 mole of the electrolyte, as the decreasing value of specific conductivity is more than compensated by the increasing value of V, so the value of lambda equivalent and lambda m increases with dilution. 6.6 Variation of molar conductivity with concentration for strong and weak electrolytes. As already mentioned in the beginning of this session, there are two types of electrolytes, namely strong electrolytes and weak electrolytes. The variation of molar conductivity conductance with concentration or dilution for such of these electrolytes is briefly discussed below. Conductance behavior of strong electrolytes. As discussed later in more detail in 6.13, the molar conductivity of strong electrolytes is found to vary with concentration according to the equation lambda m power c is equal to lambda naught m minus b root c, where b is the constant depending upon the type of the electrolyte, the nature of the solvent, and the temperature, and lambda naught m is the molar conductivity at infinite dilution, called limiting molar conductivity. This equation is called the Haber-Huckel-Ohmsager equation and is found to hold good at low concentrations. Thus, if lambda m is plotted against root c, a linear graph is obtained for low concentration, but it is not linear for higher concentrations. As shown in figure 6.5, in which KCl has been taken as an example of a strong electrolyte. Further, the curve obtained for a strong electrolyte shows that there is a small increase in conductance with dilution. This is because the strong electrolyte is completely dissociated in solution, and so the number of ions remains constant. At higher concentrations, the greater interionic attractions retard the motion of ions, and therefore the conductance falls with increasing concentrations. With decrease in concentrations, that is, with dilution, the ions are far apart and therefore the interionic attractions decreases, due to which the conductance increases with dilution and approaches a maximum limiting value at infinite dilution, designated as lambda naught m or lambda infinity m. Conductance behavior of weak electrolytes. As a weak electrolyte dissociate to a much lesser extent as compared to a strong electrolyte, therefore the conductance of a weak electrolyte is much lower than that of a strong electrolyte at the same concentration. This is shown in figure 6.5, in which acetic acid has been taken as an example of a weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially near infinite dilution. This is because as the concentration of the weak electrolyte is reduced, more of its ionized, thus increases in conductance with decrease in concentration is due to the increase in the number of ions in the solution. However, it does not reach a limiting value. Further, from the plot shown in figure 6.5, it is observed that the plot for a strong electrolyte becomes linear near high dilutions and thus can be extrapolated to zero concentration to get the value of a molar conductivity at infinite dilution, that is lambda naught m. However, for a weak electrolyte, such an extrapolation is not possible, as is clear from the plot of acetic acid in figure 6.5. Experimentally also, it is not possible to determine the lambda naught m value for a weak electrolyte, and it does not approaches a limiting value. The problem was finally solved by Kirchhoff, who put forward a law known as Kirchhoff law, as discussed in the next session. 6.7 Kirchhoff law of independent migration of ions. Kirchhoff studied the molar conductivities at infinite dilution lambda naught m for a number of pairs of strong electrolytes, each pair having a common cation or an ion. Then he calculated the difference of this lambda naught m value for each pair. A few of these results are given in table 6.2. Electrolyte lambda naught m at 298 Kelvin difference. Electrolyte lambda naught m at 298 Kelvin difference. KCl NaCl 149.86 126.45 23.41 kBr KCl 151.92 149.86 2.06 kBr NaBr 151.92 128.51 23.41 NaBr NaCl 128.51 126.45 2.06 KNO3 NaNO3 144.96 121.55 23.41 LiBr LiCl 117.09 115.03 2.06. It is observed that the difference between lambda naught m value for each pair of sodium and potassium salts having a common anion was same irrespective of what this ion was. Similarly, the difference in the lambda naught m values for each pair of salts having the same different anions and a common cation was same irrespective of what this cation was. In fact, column 3 in the table 6.2 gives the lambda naught m value for K positive ion minus the lambda naught m value from Na positive ion. Similarly, the last column gives lambda naught m value for Br negative ion minus lambda naught m value for Cl negative ion. On the basis of the above observation, Kirchhoff concluded that each ion makes a definite contribution to the total molar conductivities of an electrolyte at infinite dilution, irrespective of the nature of the other ions of the electrolyte. This individual contribution of an ion towards the total molar conductivities of the electrolyte is called molar ionic conductivities. As a result of these studies, Kirchhoff in 1876 put forward a generalization known after him as Kirchhoff law. It states as under: the limiting molar conductivity of an electrolyte at infinite dilution is the sum of the limiting ionic conductivities of cation and the anion multiplied with the number of ions present in one formula unit of the electrolyte. Mathematically, lambda naught m for AXBY is equal to X lambda naught AY plus Y lambda naught BX minus, where lambda naught m is the limiting molar conductivities of the electrolyte. Lambda naught AY plus and lambda naught BX minus are the limiting molar conductivities of the cation AX positive, AY positive and the anion BX negative respectively. For example, lambda naught m for NaCl is equal to lambda naught Na positive plus lambda naught Cl negative. Lambda naught m for BaCl2 is equal to lambda naught Ba positive plus 2 lambda naught Cl negative. Lambda naught m for Al twice SO4 thrice is equal to 2 lambda naught Al3 positive plus 3 lambda naught SO4 2 negative. In terms of equivalent conductivities, Kirchhoff law is defined as follows. The equivalent conductivity of an electrolyte at infinite dilution is the sum of the two values, on one depending upon the cation and the other depending upon the anion. That is, lambda naught equivalent is equal to lambda naught C plus lambda naught A. Section B. Section B. Theories of ionization and Ostwald dilution law. 6.8. Arrhenius theory of ionization or electrolytic dissociation. To explain a number of phenomena related to electrolytes such as conductance, electrolysis, anomalous behavior of electrolytes towards colligative properties, that is higher value of osmotic pressure, evolution in boiling point, depression in freezing point and lowering of vapor pressure that expected. Arrhenius in 1887 put forward a theory about the electrolytes. This theory is known as Arrhenius theory of electrolytes dissociation. The main points of this theory in a modified form are summarized below. First, an electrolyte when dissolved in water splits or dissociate into positive and negative charges particles known as called ions. The process is called ionization or more correctly electrolytic dissociation, etc. NaCl gives Na positive plus Cl negative. MgCl2 gives Mg2 positive plus 2Cl negative. Al2SO4 thrice gives 2Al3 positive plus 3SO4 2 negative. Second, the total charge carried by the positive ions is equal to that carried by the negative ions, so that the solution as an whole is electrically neutral. Third, on electrolysis, the positive ion migrates through cathode and hence are called cations, while the negative ions migrate towards the anode and are called therefore anions. Fourth, the ions formed constantly reunite to form the undissociate molecules till ultimately there is an equilibrium between the ions and undissociated molecules. Example, NaCl gives Na positive plus Cl negative. MgCl2 gives Mg2 positive plus 2Cl negative. In other words, the whole of the electrolyte may not dissociate into ions. Instead, only a part of the electrolytes may dissociate into ions. The fractions of the total number of molecules of the electrolytes that dissociate into ions is called degree of ionization or dissociation. It is usually denoted by alpha, that is degree of dissociation is equal to number of molecules dissociated by total number of molecules taken. Fifth, the degree of dissociation increases with the dilution and becomes maximum at infinite dilution. Sixth, the conductance of an electrolytic solution is due to that of ions provided by the dissociation of the electrolytes. Greater the dissociation, the higher is the conductance. Substances like mineral acids, alkalis, and most of the salts which shows a high conductance is due to the fact that they possess high degree of dissociation, that is, their molecules are almost completely dissociated into ions in the aqueous solution. Such substances are called strong electrolytes. On the other hand, substances like organic acids and base and some of the inorganic acids like H2CO3, H3PO4, etc., and inorganic bases like NH4OH, CaOH twice, etc., which shows poor conductance is due to the fact that it possesses low degree of NH4, low degree of dissociation. They are only partially dissociated into aqueous solutions. Such substances are called weak electrolytes. 7. The ions provided by dissociation of an electrolyte behaves like molecules towards colligative properties. For example, each NaCl molecules dissociate to give two ions, Na positive plus Cl negative. Hence, the observed value of any colligative properties is double that the accepted value. 8. The properties of an electrolyte are the properties of its ions. For example, the property of an acid are due to H positive ions furnished by it in the aqueous solution. Similarly, the properties of a base are due to OH negative ions produced in the aqueous solution. 6.9. Factors on which the degree of dissociation depends. The degree of dissociation of an electrolyte in the solution depends upon the following factors. First, nature of a solute. In aqueous solution, some electrolytes like acid, alkalis, and most of the salts are almost completely ionized. These are called strong electrolytes. On the other hand, some electrolytes like organic acids and base and some inorganic acids and base ionize only to a small extent. These are called weak electrolytes. Second, nature of solvent. Every solvent has some definite value of the dielectric constant, which is defined as the power of weaken or cut of the force of attraction present between the ions of the electrolyte. Water has the highest dielectric constant. Thus, the dissociation of an electrolyte is maximum in water as compared to that in the other solvents. Third, concentration. Degree of dissociation of an electrolyte increases with dilution and becomes maximum at infinite dilution, that is zero concentration. Fourth, presence of a common ion. The degree of dissociation of an electrolyte decreases when another electrolyte is present which furnish a common ion. This effect is small common ion effect. For example, dissociation of NH4OH decreases in the presence of NH4Cl. Fifth, temperature. As the temperature is increased, more the molecules split into ions, that is, degree of dissociation increases. Ostwald dilution law. According to Arrhenius theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and undissociated molecules. For example, for a binary electrolyte AB, we have Ostwald in 1888 pointed out that the law of chemical equilibrium can be applied to the ionic equilibrium. As a result, he obtained an important relationship known as Ostwald dilution law. Suppose the initial concentration of the binary electrolyte AB in the solution is C mole per liter and alpha is the degree of dissociation, then we have AB equilibrium A positive plus B negative. Initial concentration C mole per liter 0 concentration at equilibrium C minus C alpha mole per liter. C into 1 minus alpha. Applying the law of chemical equilibrium, we get K is equal to A positive B negative divided by AB. C alpha into C alpha divided by C 1 minus alpha. K is equal to C alpha square divided by 1 minus alpha. Exact formula. The equilibrium constant K for the equilibrium AB, A plus B negative is called the dissociation constant or ionization constant of the electrolyte AB and may be represented by Kd or Ki. Like any other equilibrium constant, Kd is constant only at constant temperature. The unit of Kd will be same as those of the concentration C. If the degree of dissociation alpha is very small, as in usual the case for weak electrolyte at ordinary concentration, alpha can be neglected in comparison to 1 in the denominator of expression 1. Then the appropriate formula becomes Kd is equal to C alpha square or alpha square is equal to Kd divided by C. Alpha is equal to root Kd divided by C. Approx formula. Second equation. First and second are the two expressions of Ostwald dilution law. Expression 2 can be represented in words as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of the initial molar concentration. Further, as C is the concentration in mole per liter, therefore the volume V of the solution containing 1 mole of the electrolyte will be 1 by C liters. Putting 1 by C is equal to V, the expression first and second can be written as Kd is equal to alpha square divided by 1 minus alpha V and alpha is equal to root Kd into V, where V is the volume of the solution in liter containing 1 mole of the solute. Thus, Ostwald dilution law may also be defined as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is directly proportional to the square root of volume in liter containing 1 mole of the electrolyte. Validity of Ostwald dilution law. To test the validity of Ostwald dilution law, that is to verify the law experimentally, the degree of dissociation alpha was determined from conductance measurement using the formula alpha is equal to lambda C divided by lambda naught at different concentration for a number of electrolytes. For each electrolytes, the data were fitted in equation first to see whether the value of Kd comes out to be constant or not. It was observed that First, the value of Kd comes out to be constant only for weak electrolytes, and that too when the concentration of the solution is not too high, that is for dilution solution only. Second, the value of Kd does not comes out to be constant for strong electrolyte. Thus, it may be concluded that the Ostwald dilution law was valid only for weak electrolytes in dilute solutions. That is why it is called dilution law, and it does not hold good for strong electrolytes. As an example, the result of weak electrolytes, namely CH3COH, and those of strong electrolytes, namely KCl, are given in Table 6.2 below. Table 6.2, dissociation constants of CH3CO and KCl at different concentration using Ostwald dilution law. CH3COOH KCl, C mole per liter, alpha Kd, C polymer meter, alpha Kd, 1.011 into 10 power minus 3, 0.00372, 1.405. 1.0 into 10 power minus 3, 0.7565, 2.350, 0.0316 into 10 power minus 3, 0.0239, 1.846, 0.02 into 10 power minus 3, 0.9234, 0.221. Importance of Ostwald dilution law. Ostwald dilution law is applicable to weak electrolytes only. As such, it is very useful in the calculation of the dissociation constant Kd of the weak acids and weak bases. By determining the degree of dissociation alpha for conductance measurement lambda C divided by lambda naught at any concentration C. Having determined the value of Kd, which is constant for a particular weak acid or weak base at a particular temperature, the degree of dissociation alpha of the weak acid or weak base can be calculated at any concentration. 6.12 Limitations of Arrhenius theory. No doubt Arrhenius theory was able to explain a number of facts and phenomena, but soon a number of objections were raised against this theory, especially when applied to strong electrolytes. A few of these objections are as follows. First, Arrhenius suggested that ionization of the electrolyte take place when dissolved in water. However, X-ray study has shown that many such electrolytes are already in the ionized state, example Na positive, Cl negative. Hence, the word ionization has been replaced by the word dissociation. Second, as an electrolyte can conduct electricity even in a molten state, it shows that the dissociation of the electrolyte take place even in a molten state. As such, the function of water could not be explained by Arrhenius theory. In other words, it could not explain why the dissociation takes place at all. Third, the most serious objection against the Arrhenius theory was its utter failure when applied to strong electrolytes. Example A. Ostwald dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails for the strong electrolytes. That is, a constant value of the dissociation constant K is not obtained. B. The degree of dissociation alpha of strong electrolytes calculated from the conductance measurement alpha is equal to lambda C by lambda naught was found to be different from that calculated from colligative properties. The values were found to be nearly same only for univalent electrolytes. C. Strong electrolytes are almost completely dissociated even at moderate concentration, that is alpha is equal to 1 or 100% at all concentrations. Hence, Arrhenius' view that conductance increases with dilution because of the dilution increases does not make any sense in case of a strong electrolyte. The increase in conductance with dilution must be therefore due to some other factors called interionic effects discussed in the next session. The ratio lambda c divided by lambda naught is therefore better called apparent degree of dissociation or conductance ratio only. The failure of Ostwald dilution law for a strong electrolyte is evidently because of two reasons. Firstly, strong electrolytes are almost completely dissociated into the solution, therefore the question of equilibrium does not arise. Secondly, the calculation of alpha from lambda c divided by lambda naught is faulty, as mentioned above. Section C. Migration of ions and transport number. 6.14. Migration of ions. When electricity is passed through the solution of an electrolyte, the ions present in solution are liberated at the electrodes, that is, electrolysis occur. This movement of ions towards the positively charged electrodes is called migration of ions. That ions actually exist independently and move with the passage of current in solution towards the positively charged electrodes can be seen experimentally as shown. Take a U-tube, fill it lower portion by CuCr2O7 jelly obtained by mixing a 5% solution of agar-agar and a mixture of CuSO foam and K2Cr2O7 and allow it to set. The jelly is green in color. To mark the position of jelly, some charcoal is scattered over the green jelly. Over charcoal in both the limbs is added KMnO4 solution in agar-agar, that is KMnO4 jelly, and then aqueous solution of KMnO4, KNO3, figure 6.10. When current is passed, blue colored CO2 positive ions are seen moving towards negative electrodes and yellow colored Cr2O7 2 negative ions are seen moving towards positive electrode. After some time, the two types of ions are seen moving with well defined boundaries. The experiment clearly shows the migration of ions. Transport number. As seen in 6.14, when an electric current is passed, the ions migrate towards the electrode. Thus, the electric current is carried by ions. Each ion carries a definite fraction of the total current depending upon its speed. The fraction of the total current carried by an ion is called its transport number or transferring number or Rittov's number. Greater the speed of the ions, greater the amount of current it will carry with it, and hence greater will be its transport number. Let UA and UC be the speed of the anion and cation respectively. Then current carried by anion is inversely proportional to QA is equal to K equal to UA is equal to K dot UA. Current carried by the cation directly proportional to UC is equal to K dot UC. Since current is carried only by ions, that is, total current carried is equal to current carried by anion plus current carried by cation is equal to K dot UA plus K UC equal to K into UA plus UC. Transport number of anion. Na is equal to KUA divided by KUA plus UC. Na is equal to UA divided by UA plus UC. Similarly, transport number of cation will be NC is equal to UC divided by UA plus UC. Two important reactions. First, Na plus Nc is equal to UA divided by UA plus UC plus UC divided by UA plus UC is equal to UA plus UC divided by UA plus UC is equal to 1, or Na plus Nc is equal to 1. That is, sum of a transport number of anion and cation of an electrolyte is always unity. Thus, no current is lost in any other function and the whole of the current is carried by the ions. Second, Na is equal to UA divided by UA plus UC is equal to 1 divided by 1 plus UC by UA is equal to 1 by 1 plus r, where r is equal to uc divided by ua is equal to speed ratio of cation to the anion. Similarly, Nc is equal to Uc divided by Ua plus Uc is equal to Uc divided by Ua divided by 1 plus Uc divided by Ua, or Nc is equal to R divided by 1 plus R. Thus, N is equal to Ua divided by Ua plus Uc is equal to 1 by 1 plus R. Nc is equal to Uc divided by Ua plus Uc is equal to R plus 1 plus R. Second, moving boundary method. This method is based upon the fact that the transport number of the cation and the anion are given by Nc is equal to Uc divided by Uc plus Ua and Na is equal to Ua divided by Uc plus Ua. Thus, by determining the speeds of the cation and anion, the transport number can be calculated. The apparatus used is shown in figure 6.14. It consists of a long tube mounted vertically and fitted with a platinum electrode on two sides as shown in figure 6.14. The salt Ba under investigation is made into a solution and then placed between the solution of two other salts B-A and Ba-, one having a common cation and the other having common anion. For example, if Ba is KCl, B-A may be LiCl and Ba- may be CH3COOK. The three solutions are arranged in order of increasing density downwards to avoid solution mixing effect. The original boundaries are A and B. Even if the solution are colorless, the boundaries can be observed because of the differences in the refractive indices of the solution. In order that the boundaries may remain sharp throughout the experiment, B dash and A dash must have smaller velocities than B and A respectively, so that B dash does not overtake B and BA dash does not overtake A. When the current is passed, the boundaries move to A dash and B dash. Thus, speed of the cation B positive UC inversely proportional to length A dash. Speed of the anion A negative UA inversely proportional directly proportional to length B dash. Hence, Nc is equal to A dash divided by A dash plus B dash, and Na is equal to B dash divided by A dash plus B dash. 6.18 Factors on which transport number depends. It has been stated earlier that the transport number of an ion is directly proportional to the speed of the ions, which in turn depends upon a number of factors. Example: first, nature of the ions. Normally, the smaller the size of the ions, greater is its speed, and hence higher is its transport number. For example, the transport number of H positive ion in 0.1 N HCl is greater than of Na positive ion in 0.1 N NaCl or K positive ion in 0.1 N KCl, etc. Second, nature of other ion present. For example, the transport number of Cl negative ion in HCl is different from that of Cl negative ion in NaCl. This may be explained as follows. NCl negative NHCl is equal to UC negative divided by UH positive plus UC negative. NCl negative and NaCl is equal to UC negative divided by UNA positive plus UC negative. Whereas UH positive, UNA positive and UCl represented the speed of H positive ion, Na positive and Cl negative ions respectively in their respective solutions. Third, hydration of the ions. The speed of the ions and hence its transport number is very much affected by the hydration of the ions. For example, Li positive ions are smaller in size than Na positive ion and hence may be accepted to have higher transport number than Na positive ion, but the actual position is otherwise. This is because Li positive ions are more hydrated than Na positive ions. Similarly, Na positive ions have a smaller transport number than K positive ions. Fourth, concentration. The transport number of an ion changes with concentration, but the change is very small. However, in case of the increase of concentration results in the formation of a complex ion, the transport number changes significantly. This is explained on the basis of the formation of the complex CDI for two negative ions at higher concentration as follows. KDI2 gives KD2 positive plus 2I negative aqueous. CD2 positive plus 4I negative gives CDI for 2 negative. Temperature. As the temperature is increased, the ions tends to approach a transport number value. Approaches a transport number value of 0.5, that is, at this temperature equal fraction of the current is carried by the cations and anions. In case of ions having transport number less than 0.5 at ordinary temperature, transport number increases with increase of temperature. In case of ions having transport number greater than 0.5 temperature. Sixth, interionic effects. How the speed of the ions is affected by the interionic effect has been discussed in section 6.13 under de Haber-Huckel theory. Section D, application of conductance measurement. 6.19, introduction. Let us first recapitulate a few terms, relation and concept related to conductance. First, conductance. It is the reciprocal of resistance. Its units are ohm inverse or mHos or Siemens S. Second, specific equivalent and molar conductivities. The conductance of 1 cm³ of the solution is called specific conductance. It is represented by K or kappa. Its units are ohm inverse, centimeter inverse. The conductance of a solution containing 1 gram equivalent of the electrolyte dissolved in VCC of solution is called its equivalent conductance. It is usually represented by lambda V or lambda C at dilution V or concentration C. At infinite dilution, it is represented by lambda naught or lambda infinity. Its units are ohm inverse, centimeter square, gram equivalent inverse. The conductance of a solution containing 1 mole of the electrolyte dissolved in VCC of the solution is called its molar conduction. It is usually represented by lambda m. At infinite dilution, it is represented by lambda naught m. Its units are ohm inverse, centimeter square, mole inverse. Third, relationship between equivalence conductance and specific conductance. Lambda V is equal to K into V, or Kc is equal to 1000 into K divided by C. Gram equivalent liter inverse is equal to 1000 into K by normality, where V is equal to volume of the solution in Cc containing 1 gram equivalent of the electrolyte. Fourth, relationship between molar conductance and specific conductance. Lambda m is equal to K into V, or lambda m is equal to 1000 into K divided by C. Mole liter inverse is equal to 1000 into C by molarity, where V is equal to volume of the solution in Cc containing 1 mole of the electrolyte. 5. Kirchhoff's law. It states as follows: the equivalent conductance of any electrolyte at infinite dilution is the sum of two values, one depending upon the cation and the other upon the anion. Mathematically, lambda naught is equal to lambda C positive plus lambda A negative, where lambda naught is the equivalent conductance of the electrolyte at infinite dilution, whereas lambda C naught and lambda naught A, that is the individual contribution made by the ions towards the total equivalent conductance of the electrolyte at infinite dilution, are called ionic conductance. In terms of molar conductance, for an electrolyte AXBY, lambda naught M is equal to X lambda naught A positive plus Y lambda naught B negative. It is interesting to point out that though all electrolytes are completely dissociate at infinite dilution, let their molar conductance at infinite dilution vary widely. This is explained on the basis of large differences in the speeds of the ions. For example, molar conductance of HCl at infinite dilution is much larger than that of NaCl. chloride being a common ion, the difference in evidence due to the larger speed of H positive ions than Na positive ions. Sixth, ionic mobility. As the speed of an ion also depends upon the potential difference applied, hence their term ionic mobility has been introduced, which is defined as follows. The ionic mobility is the distance traveled by an ion in centimeter by second under a potential gradient of 1 volt per centimeter. That is, ionic mobility is equal to speed of the ion divided by potential gradient applied. Seventh, relationship between ionic conductance and ionic mobility. As explained above, the terms ionic conductance differ from the term ionic mobility. The two are found to be related according to the equation. Ionic mobility is equal to ionic conductance divided by 96500, in which ionic mobility and ionic conductance are the limiting values, that is, when the solution are very dilute so that the electrolytes is completely dissociate. Consider a solution containing 1 cm3, the shaded faces being electrodes as shown in figure 6.16. Then the conductance of the solution is equal to specific conductance. If potential of 1 volt is applied between the electrodes, current flowing through the solution is equal to 1 by R by Ohm law. 1 by R is equal to conductance. If the concentration of the solution considering above is C, and if it is assumed that C is so small, then the substance is completely ionized. That is, we know that equivalent conductance lambda naught is equal to specific conduction K divided by C. K is equal to C lambda naught, but lambda naught is equal to lambda naught C plus lambda naught A by Kirchhoff's law, where lambda naught C and lambda naught A are the ionic conductance of the cation and anion respectively at infinite dilution, but specific conductance K is equal to the current flowing through the solution. Hence, current flowing through the solution is equal to C lambda naught C plus lambda naught A. Now, if U naught C plus U naught A represent the absolute velocity of the cation and anion respectively, it means that all the cations within a distance of U naught C centimeter from the cathode will move to it 1 second. Similarly, all the ions within a distance of U naught A centimeter from the anode will move to the anode in 1 second, as the solution consists of C gram equivalent. By Faraday law, for every 1 gram equivalent of the ion discharged, 96500 coulomb 1 F of current flows through the solution. Hence, for discharge of Cu naught C plus U naught A gram equivalent current flowing through the solution. 96500 into C U naught C plus U naught A is equal to C lambda naught C plus lambda naught A. U C lambda naught C is equal to lambda naught C divided by 96500 plus lambda naught A is divided by 96500. This leads to the result U naught C is equal to lambda naught C divided by 96500, and U naught A is equal to lambda naught A divided by 96500. Applications of Kirchhoff's law. Application of conductance measurement. First, determination of equivalent conductance and infinite dilution lambda naught for weak electrolytes. As already mentioned, the equivalent conductance of a weak electrolyte at infinite dilution cannot be determined experimentally. Firstly, because the conductance of such a solution is low, and secondly, because the dissociation of such an electrolyte is not complete even at very high dilution. The equivalent conductance of such an electrolyte at infinite dilution can be calculated using Kirchhoff's law in any one of the following two ways. First, considering the example of acetic acid CH3COOH as a weak electrolyte. Lambda naught CH3COOH is equal to lambda naught CH3CON negative plus lambda naught H positive. This equation can be derived at by knowing the equivalent conductance and determinate dilution for a strong electrolyte KCl, CH3COOK and HCl as by Kirchhoff law. Lambda naught KCl is equal to lambda naught K plus lambda naught Cl negative. Lambda naught HCl is equal to lambda naught H positive plus lambda naught Cl negative. Considering the example of acetic acid, again we have by Kirchhoff law lambda naught CH3COH is equal to lambda naught CH3CO negative plus lambda naught H positive. Each of the ionic conductance lambda naught CH3CO negative and lambda naught H positive can be found from the measurement of transport number and equivalent conductance and infinite dilution of a strong electrolyte containing that ion. Second, determination of ionic conductance and absolute velocity of ions, that is ionic mobility. Using Kirchhoff's law, the expression for the calculation of ionic conductance has already been given in section 6.19. Knowing the value of ionic conductance, the ionic mobility can be calculated using the expression ionic mobility U is equal to ionic conductance lambda naught divided by 96500. The determination of degree of dissociation. According to Arrhenius' theory of electrolytic dissociation, the increase in the equivalent conductance with dilution is entirely due to the increase in the dissociation of the electrolyte. The equivalent conductance and infinite dilution being maximum because the dissociation is almost complete. Thus, if lambda C is the equivalent conductance of a solution at any concentration C and lambda naught is the equivalent conductance at infinite dilution, will have for determination of dissociation constant Ka of acids. Considering the weak acid Ha, suppose we start with its initial concentration equal to C mole liter inverse and alpha is the degree of dissociation, then we have H gives H positive plus A negative, initial concentration C mole liter inverse, concentration at equilibrium C minus C alpha C into 1 minus alpha. Applying the law of chemical equilibrium, we have Ka is equal to H positive A negative divided by Ha gives C alpha into C alpha divided by C 1 minus alpha, C alpha square divided by 1 minus alpha. Thus, knowing the degree of dissociation at the constant concentration C, the dissociation constant Ka of the acid can be determined. The value of alpha can be obtained from conductance measurement as explained in application 3. Alpha is equal to lambda C by lambda naught. The equivalent conductance at concentration C, lambda C, can be obtained from the expression lambda C is equal to K into 1000 by C, where K is the specific conductance. The equivalent conductance at infinite dilution lambda naught can be obtained by applying Kirchhoff's law. 5. Determination of ionic product of water. Ionic product of water Kw is defined as the product of H positive ion concentration and OH negative ion concentration in gram ions or mole per liter. That is, H positive OH negative is equal to Kw. The value of H positive and OH negative in pure water at 25 degrees Celsius can be calculated from conductance measurement as follows. Ionic conductance of H positive ions and OH are found to be lambda H positive is equal to 349.8 ohm inverse centimeter square. Lambda OH negative is equal to 198.5 ohm inverse centimeter square. Lambda naught H2O gives lambda naught H positive plus lambda naught OH negative is equal to 548.3 ohm inverse centimeter square. As water dissociates to a large small extent to give H positive ions and OH negative ions, water may be considered to be a very dilute solution of H positive ions and OH negative ions in water, so that we have conductance of water, specific conductance of water into volume in cc containing 1 gram equivalent of ions. Volume in cc containing 1 gram equivalent of ions, equivalent conductance of water divided by specific conductance of water is equal to 548.3 into divided by 5.54 into 10 power minus 8. that is 1 cc of water containing H positive ions or OH negative ions is equal to 5.54 into 10 power minus 8 divided by 548.3 is equal to 1.01 into 10 power minus 10 gram equivalent. 6. Determination of the solubility of sparkling soluble salts such as AgCl, BaSO4, PbSO4, etc., which are considered to be almost insoluble in water, do dissolve in water, though to a very small extent. That is why these salts are called sparkling soluble salts. The solubility of such salt, which cannot be found easily by any other method, can be calculated by application of Kirchhoff's law and conductance measurement as follows. Specific conductance of the solution is determined. Suppose it comes out to be K if S is the solubility of the salt in gram equivalent per liter, so that the volume of the solution in cc containing 1 gram equivalent will be 1000 by S. Then equivalent conductance of the solution is equal to specific conductance into 1000 by S. Lambda is equal to K into 1000 by S. Since the salt is all very light, the solution is very dilute, so that lambda may be considered as equal to lambda naught, that is equivalent conductance and infinite dilution. Hence we have lambda naught is equal to K into 1000 by S, so that S is equal to 1000 into K divided by lambda naught. The value of lambda naught can be found by the application of Kirchhoff's law. Example for AgCl, A naught is equal to lambda Ag plus lambda Cl negative. The solubility in gram liter can be obtained by multiplying S with the equivalent weight of the substance. Thank you.